Welcome to Java Programming 3 Session 2. We're going to have a much more theoretical class today. I want to have a session that teaches more than something that is just going to be around for a couple of years. To be fair, a lot of the frameworks from Java, like JUnit and things like that, Java is such a mature technology that it is unfair to say that actually everything is going to expire. But the theory is actually much more valuable, and that's what I want you to take with you. So we're gonna make this about Java at some point, but the theory should translate to pretty much any single programming language, because these are concepts that I think that every programmer should know. We're gonna be talking today about design patterns. What are they? How are they classified? How do you choose the right one? And their main categories, which is creational, structural, behavioral, and then we're gonna at some point have some exercises. What are the design patterns, or why should we have design patterns? Well, design patterns is actually something that a group of 4 engineers that were called themselves the Gang of 4 came up and put together in this book. You can see it's one of those books that it's even hardcover. It was written in 1994, so this is before Java. This is before Java, but it's the main thing about this is that this book essentially hasn't expired. I mean, it's more than 94, 2004, 2014, 24 years after it was written in Mountain View, California, August 1994. And it's still one of the solid foundations of computer science. So the Gang of 4, which is the 4 authors of the book, after working with software and with some of the problems of object-oriented programming, they noticed a series of repeating patterns, and they decided to classify them and document them. So design patterns, they are solving problems that have occurred quite often and help us achieve one of the main goals of software design, which is do not repeat yourself. And that means that you're improving reusability, and also you're not reinventing the wheel every time that something happens. Okay, so what are the basic ingredients of a design pattern? Well, a design pattern has 4 parts: the name that describes them, the problem that they are solving, the solution that they are aiming to correct, and the consequences, meaning what are the trade-offs, the pros and cons of applying it. In the problem, we are dividing it, or in the book and everywhere that it's documented, pretty much they divide the problem into the intent, what is being solved. Some other aliases that sometimes you might see somebody calling some of these patterns something else. The motivation for the problem, and the applicability. How do you apply this to an actual problem? The solution portion describes the participants, meaning what are the entities that are involved in solving this parameter. And sometimes a design pattern is not just one class, it's a collection of classes solving one problem. So each one of those classes or interfaces that it defines as far as abstract data, abstract objects, how do they participate in solving the problem? It also defines the collaborations and how to implement it, or a high-level overview of how to implement it, because this is very general for software developers, that it's not really written in just for one language. It's been reused over and over and over again. Okay, so there's 2 ways of of organizing design patterns. It's either by purpose or by scope. And by scope, meaning where in the do they live? You know, it's more like an instance class or an instance member or a static member. The same thing in the design pattern. Where is it going to solve it? Is it going to solve it at the class level, or is it going to solve it at the object level? The purpose, on the other hand, is defining three main categories. Those three categories are creational, how do we create objects; structural, how do we organize those objects; and behavioral, how do those objects interact and behave within each other. In the creational side of things, in the class area, we have the factory method. We're going to talk about it in a little bit. In the object scope of the creational purpose, in the object scope of the creational purpose, we have the abstract factory, the builder, the prototype, and the singleton. And for those of you that have taken already Java 1 and Java 2 with me, the singleton is something that is going to, you probably have heard in my previous classes. If not, don't worry, we're going to cover it here. Then we're going to classify on the purpose of structural, the adapter for class scope, the adapter also for object scope, bridge, composite, decorator, facade, flyweight, and proxy. A lot of these names will make more sense as we are reviewing them. But right now, more or less, realize that these are the categories that they are organized. And then on the behavioral, we're going to have on the class side the interpreter or the template. And on the object scope for behavioral purpose, we're going to have the chain of responsibility, iterator, mediator, memento, observer, state, strategy, and visitor. So, two things to notice here. In certain programming languages, including in Java, there's already classes that are called iterators built into this. So, Java is already using a lot of these patterns, or some other classes that actually also have the name factory. Java is already using some of these patterns to describe some of the objects that are shipped with Java. This is what I mean by it's so common that architecturally it makes sense to reuse these patterns to solve some of the problems as best as we can. In the case of Python, for example, like there's decorators built into the language. So, that kind of stuff, like it's reused all over the place. So this is an important class because it helps you to gain a skill set that you're not going to use only in Java, but also with any other programming language that you learned. Okay, so design patterns help us to design applications. And the way that it does it, the way that it is going to help us is that it's helping us to find the correct objects that we're going to use to create the class. We're going to be also breaking down some of those objects to some more granular pieces of information. That way we can organize them better. We can specify interfaces so that we have, if you remember from previous classes, an interface is more it's on the less code of the spectrum. There's this little chart I really like drawing, which is how much code, full code, and then you have, let's choose another color. Full code or complete code and no code at all. And the more you're in the abstract layer and the concrete layer, let's even not call it abstract so that it wouldn't confuse anybody, because there's a keyword called abstract that it's related to this, but not so much, not 100% that it could actually confuse somebody. So let's call it concrete and ideas. Okay? So if there's absolutely no code, then you are writing an interface. And then if you are writing where the code is complete, you're writing a class. And if you are somewhere in between, like some code, then you are writing an abstract class. Abstract class. So if you have some code, you're writing an abstract class. If you're writing all the code, it's an actual class. And if there's no code, just the description is an interface. So why write interfaces? Well, an interface is when you are an interface is when you are trying to write something that complies to let's draw like a piece of a puzzle. That's an ugly piece of puzzle. Let's do a piece of a puzzle, or defining actually. So you have your puzzle, and you are defining. Actually, no, let's not delete those lines fully. Let's say that we are going to define how those pieces interact. So you have something like that is a little bit more defining where the piece goes, so that doesn't matter that you have anything here. Doesn't matter that you have anything here, any type of implementation. You know that in order for your code to work, you're essentially creating the space or the way that your code will comply. So doesn't matter how you write it, as long as it has that shape. Doesn't matter if at the end of the day you wrote something that is like this and it has a blue color. It's still a piece of the puzzle. Or if you wrote something that looks the same way, but it has multiple colors. So you have stripes, and then you would have something like this. It's still compatible with that. And that's where interfaces help us. It makes us define compatibility layers. And this is just a quick reminder of Java 1 and 2. And why would we define certain compatibility layers? Well, compatibility or interfaces, they help us for two things. One, when you are writing code for somebody else, code for someone else. And two, when you are trying to keep code flexible. That means that at some point in time, you want to be able to expand on this, and you can add something without having to rewrite everything. And when you're writing code for somebody else, it's essentially the same thing. You're making it flexible. It's the interfaces is defining flexibility. Flexibility. I wrote like my son in a wook. and here is like more rigid, if you will. So here on this side that is more rigid, if you want to change something, most likely you would have to rewrite it. And if in this case you are defining a little bit more flexibility. So depending on how much flexibility you want to have in your code, you would use a combination of these two concepts. Or in other words, this concept and this concept, and you would blend them somehow depending on where you want to make your code more flexible or not. So this is where, again, design patterns help us, because they are helping us to specify such interfaces to make the code more flexible. They are also defining, given those interfaces, how the objects are implemented, and they could help us with reusability, which is the next point. It's defining the reusability early on, so that way if we decide that we want now another piece of the puzzle that is diagonal lines, that has diagonal lines and purple background, we can do that because we can define the reusability of the entire rest of the puzzle, and it still connects properly. And given that flexibility and reusability, it helps us design for change, because at some point the code that we wrote, it might be great and perfect, but it might not be intended what the user wanted or needed, or how technology or society has evolved. So we have to be capable of designing for change. Okay, so given the big menu of patterns, you might feel a little bit overwhelmed on how to translate it from the world of I've got a problem to, okay, how do I go about getting one of the patterns from this book and choosing wisely? So here are some tips on how to select some patterns. So first of all, I mean, and the main thing here is to go and read some of them. Right now, this class is not really intended for you to memorize all of them. I'm not going to make a quiz of like, tell me exactly what is the difference between the abstract factory and the builder. I'm not going to be asking you those things. I just want you to be aware that these things exist, so that way you can make solid decisions as a programmer. So the first thing is just see how they resolve certain problems. There's a portion on each part that is called the intent, and even let's see, like I think that if we went on a Wikipedia hunt, and let's just bring here and let's do a builder pattern, and there's gonna be the Wikipedia. It's going to have like some good examples for different languages, all of them, but it does have the overview, the definition, pros, cons. Not exactly in the same way that the book actually goes and defines all of them, but at the very least it can give you a solid idea of the design patterns. And you can see like here is what I'm talking about, like the design patterns and the document, like a basic documentation. So really, ideally, yes, the book is great and everything, but ideally you really don't need to spend the money because all that information is available online. But how do you get to that information online if you don't know that it even exists? Well, that's what I'm here for, to tell you how to Google design patterns. Okay, so look at the intent, look at how it's trying to solve a problem. Learn how it interrelates to other patterns in the same way. Consider patterns that have a similar purpose and compare them and see which one fits the best your strategy. So sometimes, like, that you want to separate abstraction from implementation in the creation of an object. Well, let's look at some creational objects and see how the pattern might prevent redesigning some of those problems, and also how that pattern affects the design flexibility. So those are the things to keep in mind. All right, so we're gonna get to the meat and potatoes of the design pattern class, where we're starting to talk about more or less what each pattern does and what do they do and how do they interrelate with each other. So in the first category, on the purpose side of the pattern, we're going to review the creational patterns. And for that, we have the abstract factory, for example, which is a factory of factories. It's essentially a way of decoupling the creation, so that way you can create several families of the same type of object. So, for example, you can create different abstract factories if you were creating cars. And which ones would be those factories? Well, one would be make a Toyota, the other one would be make a BMW, the other one would be make a Honda, the other one would be make a Volkswagen and an Audi, and all the brands that you want. And it would be too much to put them on one single type of factory or one single object. So you can use the abstract factory to abstract the creation regardless of which one of all the brands that you're going to create a car from. The next pattern is the builder pattern, and we're going to be reviewing it, and we're going to be doing a code sample on this. But it's basically like a wizard on a software installation or on a car dealership. It's a step creation where multiple parameters are needed, and we're going to be talking about this in a little bit, so I don't want to spend too much time on this. Factory method, also we're going to be looking at the factory method in doing an exercise together. And in here it's closely related to the abstract factory, but this is more just for a method where you have different subclasses and you allow them to define how they're going to set up the general object. So, for example, from car, the subclass would be Audi car, and the Audi car is going to decide how it's going to create a car object. Prototype is something that in JavaScript has become. JavaScript is not really an object-oriented language. It uses prototypes, which you define the object prototype, and then from there you can clone that prototype to create an object. But that doesn't necessarily mean that you have all the proper object-oriented capabilities of like encapsulation or inheritance, etc. So prototype is just essentially you define how the blueprint is going to be, and then from an instance of an object you're going to copy it. It's different than class instantiation or class creation from an actual object, because there you only have the blueprint. In a prototype, you have the actual object. So from the traditional Java method, you are creating the object from the class by saying new object. And in a prototype, you already have that object. You're just copying it around. And the last creational pattern is a singleton, which help us to control the amount of instances that we create. One thing to keep in mind with creational patterns is that there's a range so that it can help us choose, because a lot of them, they all create objects. But we are having certain trade-offs. And the main trade-off is simplicity. And the easiest one, obviously, is to, not have a creational pattern if you're doing like just a traditional object. But if you have something where you need a mechanism for building things from outside and having consistent objects created, the factory method is going to be the simplest. Because you're letting a subclass define how the top class is going to be created. It's like essentially a factory method allows a child to say how the parent is going to exist. And when you need that, that's the simplest way. When you need more complexity, well, Abstract Factory, Prototype, and Builder method are significantly more complex, or add more complexity to creating them properly, but at the same time are more flexible. So depending on what you're looking for, simplicity or flexibility is your answer may lie somewhere in between. So then let's talk about a little bit of the factory method and why are we what's a good example to try to understand the factory method. So you might know, if you have ever worked with color, that color is really defined by multiple color spaces or recipes for color. So one of those is the hue, saturation, and luminance method, which the hue is just a circle that in 360 degrees it defines, the from red to orange to yellow to green to blue to purple back to red. The second dimension would be the saturation, how rich the color is, and the luminance, how dark or light that color would be. The other method is more for like ink, so or printed mechanisms, where you are adding color together, and the addition of all color becomes black, or really dark in that sense, where you have the basic colors would be cyan, magenta, and yellow, and black. So CMYK, that's how you can define a combination of all colors. The next one is another method of, but that how color is created via light, which the sum of all the colors is white. So, for example, if you add a spotlight with red, a spotlight with green, and a spotlight with blue, perfect colors of those, then you would have white light. And that is also what is a principle on TVs, RGB, or monitors, or anything that is a computer screen usually operates on the RGB color space. And then we have other methods like YUV and things like that, which are more for like video and NTSC color spaces. But this is all just to say that we have 4 different recipes for 4 or more for creating any color. So if you want to achieve, say, a salmon color, well, in some printing cases, you might have a Pantone. In some other cases, a Pantone number. In some other cases, you might have the coordinates of a CMYK thing or an RGB and an HSL. And how do you convert between all those? So the factory method allows us to create different instances of the color object given different methodologies of creating them. Let's assume that if we wanted to create them, why would it be important in this case? For example, if we wanted to create them via a constructor and we received values, 3 integers with values from 0 to 255, which is usually what in RGB 8 bits it's defined, and the same thing for HSL in 8 bits. I mean, there's bigger versions of that, but for simplicity, let's just say from 0 to 255 of R, 0 to 255 of G, and 0 to 255 of B. It could get confusing for the constructor to know if you are trying to create a color via RGB colors or HSL colors. If you're calling get new color and then 3 integers, which one is it? So the factory method allows you to block helps you to differentiate that and be able to create a color by making the constructor private. You can create the methods and control those via the method names. So that's an important thing. And in some of our code samples, actually, if we go into the this will be on the website, but if you go into patterns creation and we go into the color factory, I have created an internal class called color, which, because it's private, I can just block how it's accessing. So it's I know that for all the reasons I'm going to generate an like hue saturation luma, which is HSL. I'm going to create those this way, and it does. And then here in the color factory, I'm going to make an RGB color, and I'm going to receive the 3 integers that actually represent it. And then internally, I'm going to control that I'm going to convert from RGB to HSL, which is this method here, this math formula. And then I can just straight up do a, let's make it for more consistent. I make it HSL color, where I'm receiving the same three integers, not the same, but they have different intention, but 3 integers. But the fact that there's a different method, a different factoring method, it allows me to have the flexibility to create colors in the right way. And here's some of the code. Okay, so the builder pattern here is mostly for wizards or things like that they're quite common when you're installing software and you have to have certain parameters, or in this case, and it's very common for car manufacturers to drive you through the process of finding your perfect car by doing a wizard. So here I just decided to put the steps of the Tesla website, where you can choose all the parameters of the things that you want to build. So once you have all those parameters, the idea here is that you might have, if you were going to do it via a constructor, and let's go into IntelliJ, and let's say that on the let's just create, this was builder. Let's on the creation, let's build car builder, and we have a protected, or let's say private class Tesla. Let's call it Tesla builder. And if we wanted to define, I don't know, like int cubic, like the let's even look at the actual parameters, and let's just let's just constructor. Let's just make sure that let's go into the order now. And in this case, we could choose the performance or the battery. So the first thing is we're going to go into battery, int battery type, and just let's say that it's 1. The other parameter, let's say the color C, paint color, and then we also have the wheels. And right now I'm faking the classes. That's why they're red. But interior, I don't know, it's a color. Interior color. And then let's say Boolean autopilot. And let's say that so if we wanted to do this via a traditional constructor, we could be doing like public Tesla, and then in battery type uh, color, paint color, wheels, wheel type, color, interior color, and then Boolean autopilot. This is a little bit long. I mean, and you know, other configuration things for other cars, like let's say Audi. Let's just go into the Audis, or BMW or something like that. So let's just choose models, and let's grab models. Let's grab, I don't know, the Q3. It's the first one, and let's try to find the constructor. I think, well, let's not waste too much time on this. So we do have a lot of arguments here, and it becomes unreadable even if we wanted to do something like this. Imagine if it's 20 parameters, you know, rather than just 5. If it's 20 parameters, what you actually need to like build your perfect car, you know, you could be asking for like bigger engine and I don't know, butt heating things, and I don't know, like cars have so many options these days that just creating something like this would be impossible and like tedious to actually create. So a builder class helps us to say, to do it via setters. Set public void set color, and then we do color C, and then this dot paint color equals C, and then public void set interior color C, and then let's do this dot interior color equals C, and so on. And then at one moment you would do something like public Tesla build Tesla, and here you could do like even try catch. I'm thinking in Python. Thank you very much. You can do build exception E, and let's do even like a private class build exception extends exception. And you know, like you can do something like, if we don't say have a color, you can't really build it. This dot color paint color is null, then raise actually even not even in a try catch, let's just do it so that way you could potentially say throws build exception. And you can do it with all the parameters somehow here, but at this point you're not passing like 100 parameters. It really doesn't matter what order you call them, which in this case it does, like which order you put the parameters. You can just be building the car. And even in some cases, like set up some default, like say that the interior color, we're going to leave it as black for whatever reason, or new color black, you know. And then and then I don't know, we can do something after you do like all the parameters. You can do something like Tesla T equals new Tesla, and then T dot set paint color equals this dot paint color, and let's assume that this one had, you know, a color paint color just for consistency purposes, and then return T. And that's how you do a very basic build pattern. The last creational pattern that we're going to review is something that I've discussed for some of my former students of Java 1 and Java 2, the Singleton creational pattern. And the creational pattern of the Singleton is that you can only create and only create one single instance of the entire object. Doesn't matter how many times you call the same function for creating, you will only guarantee that there's only one instance. So in this case, we're using a static instance as a class member called instance for a singleton. We privatize the constructor to prevent somebody else from calling it, and then we create a method that is static and returns a singleton, which is called getInstance. So if the instance has not been created, then it creates a new instance. Otherwise, it returns the instance that it's already created. Okay, so let's now talk about structural patterns, which essentially they tell us that how we are going to organize ways to either compose them to realize new functionality, or how to organize them to give us more flexibility at runtime. And here we have a slightly longer list than in the creational patterns. To begin with, we have the adapter, which, like a cable adapter, a USB adapter to a Thunderbolt, or things like that. Essentially, it helps to convert one interface to another. A bridge, which decouples the abstraction from the implementation. And in the case of the bridge, we're gonna see it as a little bit of a further detail in further down, so I'm not going to stop right now on that. The composite is a way to group objects into tree structures to be treated as a whole unit, kind of like a family, that it composes a bunch of different people in parent, child, sibling, etc., to just be treated as a whole unit. A decorator, and for those of you familiar with the Python term, this is related to it, which attaches dynamically additional responsibilities to an object, such as login or things like that could be on the nature of doing before the execution of something else. A facade, which is just a way to have a unified subset of interfaces, similar to like a business facade or something like that essentially unifies things. The flight weight, which shares to support large numbers of fine-grained flight weight, which supports large numbers efficiently. The proxy, which provides us placeholder for another object to control it. This is really common in networking, and we're going to also discuss it at large ahead of time. The proxy, which provides a remote control for another object. This is really common in networking, especially, like you want to access some other server and you want to unify the request from there and just have like one exit point that's a proxy. And that pattern is actually quite useful in some other cases. For example, if you were going to design that, you could have a real connection to the internet and just replace the IP, so that way the request feels like it comes from the new server. A couple things to keep in mind with the adapter versus the bridge. A few things to keep in mind with the structural patterns. And you might have noticed that there's some that are quite similar. The adapter focuses on resolving incompatibilities. And the bridge helps on numerous implementations. And I know that this is exactly what the slide is saying, but the best way to describe it, and we're going to do it, show an example of like a Big Mac and a Happy Meal. I was doing that example while I was taking my kid to play in the structures there. Uh, I You can have multiple implementations of a Happy Meal, which different with McNuggets, a burger, etc. And how do you handle all those by having one bridge class that helps you to dynamically deal with different implementations? And I'm focusing on the bridge because I find that one quite useful. Um, the composite versus decorator versus proxy, all those three are kind of similar, but I just want to highlight some differences. The decorator just adds extra responsibilities without adding any subclassing. So you can attach certain responsibilities without having to essentially create a child object and overriding it, and with all the cons that sometimes subclassing might have. Composite, it's just it tries to aggregate things to be treated uniformly, and the proxy is more close-ended than the decorator. The decorator, like the proxy, is like essentially a one-to-one with a subject that it's dealing with. So it's very tightly related. It's like essentially a mirror of the same thing. It's just few adjustments. And the decorator is a little bit more open-ended because you can just add those extra responsibilities. All right, so let's talk a little bit about the proxy in here. And here we have a little bit of a code sample, like a proxy request, where we are essentially recreating a new request from the proxy. We're creating a completely new request, setting up the same values that the other thing had, except for the source field on the request to replace it with the local IP. In the case of the bridge, which is something I wanted to talk a little bit more about, and all these code samples are uploaded in Git, so that you guys can actually see the files and try them by yourself. I created. I don't know if you guys have seen this, but let me see if I can get to it. And it was just a good example while I was taking my kids to play at the play structure. But McDonald's was trying to clean up its act. I'm going fancy. And let's see, order station. They now have these fancy screens where you can just go in and essentially type pay, and they bring it even to your table. And I was thinking, okay, if I was going to write the software for this thing, I would probably use a bridge pattern to design a combo meal that has, meal item, fries, etc. I'm just simplifying it and just keeping it to one item. And just leave it very abstract, because you can have like the combo for a Big Mac, the combo for, I don't know what all the things are there. I just know my kid likes a chicken McNugget Happy Meal. So in this case, you can have the Happy Meal, which extends a combo meal. But how do you deal with all the internal arguments to cook the proper thing? So as you order, you're going to cook the thing, and then you have the meal item, which different meal items could be a Big Mac or McNuggets, just in this case that I'm putting this example. And if you see it this way, I'm going from this to this to this to this to this. But in reality, the main code, the entry point, is creating a combo meal, which is going to be a new Happy Meal. So I'm storing it as a combo meal, that it's a Happy Meal. This is a bridge class that is generating this class is essentially bridging the differences in like multiple instance types that it can have, as far as like the meal item for a combo meal. So the Happy Meal is actually storing a new McNugget Happy Meal. Um, so yes, the Happy Meal acts as the bridge between all the different, and we can have like 20 different meal items, and obviously the McNuggets are cooked differently than the Big Mac, and yeah. Okay. Behavioral patterns. As far as behavioral patterns go, the behavioral patterns, just like the name says, it just says how objects are gonna interrelate to each other, and they help us to define algorithms or responsibilities, and even communication between objects. Um, in the behavioral patterns, we have many. The list is also quite long. So we have chain of responsibility. So this one, a good example is like when you have, say, a waiter who go like a customer in a restaurant that places the order. The waiter puts in the command, which is the next one, a command, um, into the kitchen, where the chef sees the request and then passes it to the sous chef or to the cook, what is going to be happening. So it's a chain of responsibility where they might delegate to the chain. In the chain, things get delegated. So for example, the waiter can actually handle the drinks and go get the drinks on the command from the customer. But when the waiter cannot handle the request, he passes it to somebody else. And then you have a manager, and that manager passes it to somebody else. So there's that behavioral pattern of chain of responsibility. Seems too obvious, but it's useful to keep in mind that you can solve problems and keep your software flexible by using some of these design patterns. Command, as I was saying, you can encapsulate a request to an object. So, for example, if in a restaurant ordering system, the command is essentially the order of what you need to build. And in some cases, the command might be interpreted as just pull it from the fridge and heat it up, or cook it from scratch. An interpreter is just essentially like you can define a little mini language and have that thing interpret. The next one is interesting because the iterator is all over the Java language. And the iterator essentially is going to hide the access to the elements regardless of how it was generated. We're going to talk about this one in particular as an example in a few minutes. Then we also have the mediator, which a mediator is a way to avoid, in some cases, circular references, and that's something that compilers have a hard time when you are including the source file for one file, and that file has a reference to another file that has a reference to the first file. So then you're building this circular pattern that can be easily solved by having a mediator in between. The memento is also one that we're going to talk briefly, but it's just one that helps you capture an internal state to be then used later in time. Then we have the observer. This one is really useful in reactive programming and in also mostly like graphical user interfaces for signals and things like that. It's actually widely used then, because when the state of something changes, it can trigger the change somewhere else. Then we have the state, which essentially allows the state to alter the behavior when something changes and also to control it better. The strategy, which is how to choose, given a certain family of algorithms, which algorithms to use. So, for example, in the example of the kitchen, choosing between the drinks, like can I solve the drinks now, or can I pull the dessert out of the dessert fridge? Or should I go into the kitchen and put the command? That's kind of like the strategy. You have a family of algorithms, and you can make them interchangeable depending on what you want to do. Template method is just similar to the factory method, but for a skeleton of an algorithm. So it's kind of like it will help you to redefine certain steps in the entire algorithm, similar to what we did with the factory method. The visitor is just a class that allows you to perform an operation in different elements without really changing the initial object. So you can define new operation on the fly. The nice thing about behavioral patterns is that it encapsulates variation, so you're kind of isolating that the variation that way. You can use objects as an argument, as similar to what we saw on the bridge, but it can help us define like new strategies or figure out, like, in the case of the strategy pattern, to go and create new objects and be passed around through the objects, which leads to the next point, that the communication is encapsulated or distributed if you want to communicate better some of the objects. And it also decouples the senders and receivers. In the case of the restaurant, it decouples the customer from the waiter from the chef. And it's not all solved in the same role in the entire program. Now let's talk about a couple of examples, like the iterator. The iterator is all over written in the entire Java language, where you have they are very efficient, because rather than loading the entire array in memory, kind of like if we go into, where is this thing? Here. So kind of like if we have our memory and we have an array, in a traditional for loop, we have to load the entire thing in memory and then start going one by one on the entire array. And then, if you have enough memory, this is fine. It really doesn't matter. But then what happens the moment that you have thousands of elements and your memory only gives us a small window of data? So rather than loading the entire thing, you can just be accessing item by item by item by item until there's no more data, and the only thing that you're keeping in memory is the object where it is, and the next one, essentially. Or the iterator allows you to define how you're going to access it. So going back to the slides, it's hiding the structure internally. So it doesn't matter if you have a tree. So if we were going to do it in a post order way, we would do it. We would crawl this tree in by saying that it's A first, then C, then E, then D, then B, then H, then I, then G, then F. Completely different than the pre-order way. And to the iterator, that's in charge of figuring out how it would traverse, or even on a graph, which, by the way, that's what Facebook uses to keep relationships. It's a graph database to keep relationship of the connections and the networking and friends and stuff like that. Imagine traversing the Facebook, like some Facebook graph databases, would be impossible. So an iterator allows you to don't really care about how the data is organized, whether it's a linked list, a graph, any data structure. It would handle that, and it would be transparent for us to crawl that object. The memento is an interesting one, because a memento, you're using it every every day, all the time, every time that you use the undo key or Control Z or whatever the shortcut is in your computer, the memento is a way for you to store the current status of an object, and it has three participants: the memento, which is the snapshot; the originator, which in the case of, like, say, Excel, or which is what I was using here, is essentially some part of the program that it's going to say, okay, when I click undo, I'm going to create the memento and then store it somewhere. Somewhere meaning the caretaker, which is the safekeeper of the state. So essentially, that stack of each time I type, that is keeping a small memento of the entire document that I can go forwards or backwards depending on my current stack. And basically that's it. For a quick introduction to design patterns. I hope this brings in a little bit of a perspective of what they're used for, and a good idea of how to solve big problems that otherwise you might be reinventing the wheel and finding through several headaches that it may need to be refactored. See you next class.